Okay, thank you. Thank you. So my name's Adam Brown, as Kieran just told you. I'm a theoretical physicist and computer scientist. And the organizers asked me today to provide some the big context, some long-term perspective. So for that, I could tell you about a lot of things, but I'm going to talk about the elephant in the room, which is the cosmological constant and the heat death of the universe. So the single worst day in human history, at least in terms of expected value, was the 16th of December, 1997, when a team of scientists, two teams in fact, observing distant supernova and how they dim, put on the archive some extremely bad news, which is that they are redshifting much faster than the then prevailing cosmological model would have predicted. They are in fact accelerating away from us. So this was the discovery of what we call the cosmological constant, sometimes dark energy, sometimes accelerated expansion. All those are just words to mean that the universe we discovered is accelerating in its expansion. Up to that point, the prevailing model was that the universe is expanding. That's what sort of Hubble and friends discovered almost a century ago. But expanding at a ever slower rate, with a diminishing speed. What was discovered in 1997 is that that's not true. Is that in fact, the universe is not only expanding, it is expanding ever faster. That's what the cosmological constant tells us. And that is very bad news indeed. The reason it's very bad news indeed is that the universe is full of galaxies, as far as we can tell. We can see many of them, somewhat less than 1 trillion of them. And we really want what they have. We want to go out there, we want to get their resources, we want to eat them up, we want to turn it into happiness. Let's do it. And the reason that the cosmological constant is such bad news is that the accelerated expansion of the universe is carrying away from us all these galaxies that we want to go get. In fact, there's really bad news. If the cosmological constant is indeed constant, basically what we can see now is what we've got. We can see these sort of somewhat less than Avogadro's number worth of stars out there in the galaxy, and anything that's further away than that, we will never be able to access, because even if we send out a probe at the speed of light in that direction, the expansion of the universe will mean that it is just getting further and further away from us faster than a speed of light probe can catch up. And we're not even currently sending out speed of light probes as we speak. We're sitting around giving each other PowerPoint talks. So while we sit here, every week, approximately 2 galaxies fall over the cosmic horizon, which is to say that approximately 2 galaxies are dragged by the expansion of the universe, the accelerated expansion of the universe, out of our grasp. And that's 2 fewer for us to extract utility from. Okay, so that's like really bad news. Maybe I should just complete that thought. A finite amount, a large but finite amount of accessible energy means a large but finite amount of free energy. Every process we ever know that's ever brought happiness into the universe, brains, computers, anything you like, needs free energy in order to function and error correct. And unless that means, therefore, that eventually, unless something changes, we will just run out of free energy. We will just be a thermal empty space at thermal equilibrium. And that's known as the heat death of the universe, and that is bad. But this is the Foresight Institute, and we believe in existential hope. So let me leave you with a piece of existential hope. It's called the cosmological constant, but we don't actually know that it's constant. So this is the dark energy that's causing the accelerated expansion. It's called the cosmological constant because it's much more constant than anything else that we have observed. So, for example, planets, for example, as the universe expands, dilute a huge amount, and their effect on the expansion of the universe becomes ever less. Radiation, even more so, it redshifts at the same time, it dilutes a lot. The cosmological constant, according to our best observations, according to the supernova data and other data, is constant to about 1 part in 10 to the 2, so to about 1%, which is to say that every time the universe doubles in size, which is happening every 15 billion years or so right now, the cosmological constant doesn't change very much. According to our best models, left to its own devices, it probably doesn't change. That's why it's called the cosmological constant. But we don't have to leave it to its own devices. In every consistent theory of quantum gravity that we know about, the cosmological constant is in fact, in principle, manipulatable. That we can take it and we can bleed off the cosmological constant and extract energy from it. And I'll leave you with a little physics, which is excellent news. In fact, according to, we don't understand what the laws of physics are at the basic level, but according to our best theories, the following is true. We can take the cosmological constant and a sufficiently advanced civilization, and this is a problem for the engineers, because it is not inconsistent with our best theories of high energy physics, that one can in fact take the cosmological constant and slowly bleed it off. One could do so in a way that extracts energy from it, and in fact leads with an unbounded amount of energy in the distant future, and would avoid the heat death of the universe. Things would still be equilibrating, but because there's an unlimited amount of resources, one could still extract an unlimited amount of free energy from them before they fully equilibrate. And maybe I'll just leave you with how many minutes do I have left?
1 minute.
1 minute. So let me just, for the physicists or interested people in the room who may be interested for an analogy of how this physics process could work, you can actually do the same with an electric field. If you just have a constant electric field, there's a constant energy density. And if the constant energy density is constant in that completely constant electric field, there's energy bound up in the electric field, which is in fact very mathematically analogous. It's sort of a one-dimensional version of how energy is bound up in the 3 + 1-dimensional cosmological constant. And there's a process called Schwinger pair production, in which you can extract from the vacuum an electron and a positron, antiparticles. It conserves charge because there's a plus and a minus. And you obviously need to pay to do that. You need to pay 2mc², the cost of making an electron and a positron. But by unraveling the electric field between them, they lower the energy density between them, which is equivalent to lowering the cosmological constant. And if you put them far enough apart, you will eventually pay back the mc² cost of making the electron and the positron and extract free energy. That's something that happens, in fact, spontaneously, according to an old quantum field theory calculation, because they quantum tunnel to produce these things, but that's an insanely slow process. But there are massive lasers that exist in the world today where people create huge gravitational fields and then are able to simulate using engineering techniques the production of electron and positron pairs, and so bleed off incredibly strong electric fields that exist in these lasers. Electric fields, thank you. And this would just be a high-dimensional gravitational analog of that. So there is yet hope. Thank you.
Wonderful, thanks. Please stay up here because we have a 3-minute Q&A. And then after you ask your question, get mic'd up because you're next, Andrew. Yeah. But first ask your question.
Yeah.
Thank you very much. It was fascinating. If an extremely advanced civilization were to lead off the cosmological constant,
yes,
as you described, would there be a detectable signature of that?
That we would see? So it sort of depends how far away they are. If they're outside our current cosmic horizon, if they're more than 10 billion light years, you can't see anything, so there will be no impact whatsoever on us. If you're looking up at the sky and you're wondering whether they've bled off the cosmological constant, I don't think it's unlikely that would be the first thing you would see. But they would be using that bleed off to do, to generate lots of energy, and you could perhaps see that the energy that they use it for would be more likely. The other aspect is it's quite hard to control the bleeding off the cosmological constant in one zone. So they may end up just bleeding it off in their full future light cone. And so if that happened, you would see it indeed as a massive dipole in the night sky, maybe looking at the cosmological constant, where the wave of smaller cosmological constant would come to encompass us. And assuming it wasn't fatal, then if you looked at the CMB in one direction, it would be hotter than the other direction. So we haven't seen that yet. Yeah.
I'm not a theoretical physicist, but there's the concept of death bubbles.
Death bubbles, yeah.
Which is, if you're fiddling with a cosmological constant, I mean, the quick story is the universe might be at a metastable level.
Correct.
A quantum metastable, and if it de-excites, it rewrites everything. And there is a way to escape it, which is the good news. If you go close to the speed of light, then the expansion helps you.
Yeah, so this is a topic on which I wrote my PhD thesis, so I'm very familiar with death bubbles. Death bubbles is...
Resist mentioning it, though.
It's the bad version. So when you lower the cosmological constant into a bubble, one would hope that you do so without affecting any of the other laws of physics. That would be, as in, you affect the gravitational force, but you don't affect the electromagnetic or the strong force, because life is very well adapted that we see around us to the values of the electromagnetic field strength, the electromagnetic coupling and the strong coupling. And you change them by 1 part in the 10 to the 6, and things get very bad for chemistry. So the good news is that the laws of physics, as like string theory and other consistent theories of quantum gravity, appear to allow you to only change the gravitational coupling, not also the electromagnetic and strong coupling. But if you did change the electromagnetic and strong coupling, you would need to transmute ourselves into a medium suitable for the new laws of physics inside the bubble. Otherwise, the laws of the chemistry that we currently run consciousness on would not still operate.
Order of magnitude, what's the power density of this extraction?
Oh, incredibly strong. Yeah. So the cosmological constant is it's very dense. It's about as much as the energy density and everything else added together.
All right,
Yeah.
we'll leave it at that. Okay. Unfortunately, we have to leave it at that. Thank you, Adam. Just to explore the workshop, it could start with something like, how might we or how could we do X, Y, Z to make progress on the topic you discussed?
Yeah, if people feel qualified, I think this is a great topic to think about.
How might we?
How might we avoid the death bubble problem and ensure the life bubble problem?
How might we avoid the death bubble problem? Great. So I think you can see we're already going all out there with the first question. So feel free to go all out there as well as you'll add yours. Thank you so much, Adam. This was wonderful.